Hello, all you wonderful young people. Sorry about that. That was really loud. This is your wonderful AP Chemistry teacher, Mrs. Rains. A little crazy this morning because I've got way too many things to do and not enough time to get it done. So here we are talking about oxidation reduction reactions, okay? So what does that mean? What is an oxidation reduction reaction? Let me take myself out of here so that you can see some stuff. I'll put myself back in a little bit. Yeah, it's wonderful to look at right now. It's morning head. Okay, so here we go. Oxidation. What does that mean? Oxidation is a loss of electrons. When we lose electrons, we've oxidized. It can also be characterized by atoms increasing in charge. So that means if I go from a 0 to a +2, I've increased in charge. If I go from a -3 to a +1, I've increased in charge. If I go from a 0 to a +5, I've increased in charge. Those are all oxidation reactions. The other side of that is reduction. For every oxidation, you have to have a reduction. You can't lose electrons to the ether. You've got to lose electrons to something. So with oxidation has to come reduction. Something has to take those electrons. So reduction is the gaining of electrons. So if we gain electrons, we've been reduced. Okay? So atoms will decrease in charge when they're reduced. So for example, you could go from 0 to a -2. You could go from a +2 to a -1. You could go from a +3 to a 0. And you would be reduced. Anytime you're reducing your charge or you're gaining electrons, you would have a reduction. These are two sides of that coin. The top part, talks about the electron transfers, what's happening to the electrons and they're being transferred. The other part talks about the oxidation number and what's happening to the oxidation number. They're both very helpful, because you have to remember that you're going to need to know the oxidation number in order to understand what is happening in everything that we're going to do, which is the next step. So Leo says GER or oil rig are two mnemonic devices that we use to remember the difference between oxidation and reduction. Leo says GER says losing electrons is oxidation, gaining electrons is reduction. There's Leo saying GER right there, okay? Oil rig, same kind of concept. Oxidation is losing, reduction is gaining. And you see my little fancy oil rig right there. So those are two ways that you can help yourself remember what's happening to the electrons being transferred. Okay, so how do we know this? Well, we know it because we're going to be looking at oxidation numbers. So we have to be able to calculate oxidation numbers. They are also known as oxidation states. And you already know this. We've talked a little bit about oxidation numbers. When we talk about ionic compounds, those charges are considered to be the oxidation numbers. So you already know a little bit about this. We just have to add another piece because we're going to be assigning oxidation numbers to covalent compounds, and that's going to be a little weird for you. Okay, so an oxidation number is assigned, an assigned charge on an atom, just like in formula writing. So that's what we were talking about. My face is mixing the word in, so don't panic, okay? So rules for assigning oxidation numbers. This is how it goes. So oxidation numbers of any atoms or elements is 0. So if you have an atom or an element, it's 0, including the diatomic molecules and allotropies of things. For example, N2 is a diatomic molecule. P4 is phosphorus, and the way it comes. S8 is one of the allotropes that we find sulfur in. All of those have 0 charges. Okay, the oxidation of monoatomic ions is the same as its charge. So if I have sodium, it's a +1. If I have chlorine, it's a -1. So we keep those monoatomic ion charges that we've seen before when they're by themselves. Okay? In its compound, fluorine is always assigned an oxidation of -1. Fluorine is special, -1. If you see fluorine, it's -1. Don't even worry about it. Oxygen gets a little hanky. Most of the time we assign oxygen a -2. So in almost all cases we do, except when we have peroxides. Peroxides are compounds that contain an O2 2- group. And when that happens, the oxidation number of oxygen is a -1. So in hydrogen peroxide, H2O2, we see that oxygen has a -1 charge. In OF2, that's oxygen difluoride, the fluorine has a -2 charge, the oxygen has a +2 charge. So when we're assigning oxidation numbers for oxygen, in almost all cases it will be -2, but there are some exceptions, and you see them here: peroxides and this oxygen difluoride, because fluorine trumps oxygen in the assigning of oxidation number. Okay, 5. In its covalent compounds with nonmetals, hydrogen is assigned a +1. But in metal hydrides, for example, if I had sodium hydride, well, it would be a -1 in that case because it's the end of the chemical formula that's an ionic compound. So it is the anion and not the cation. But if we're talking about an acid, it's a +1. If it's in the front, like water, H2O, then it's a +1. So if H is in the front, it's going to be a +1. If H is in the back, it's going to be a -1 for most part. Metal hydrides means it's only hydrogen. There's nothing else with it. It's just hydrogen. Okay, the sum of the oxidation numbers must be 0 for any neutral compound. For polyatomic ions, the sum of the oxidation numbers must equal the charge of the ion. So this makes it pretty easy to determine these oxidation numbers, because we have to remember compounds have a neutral charge. There is no charge unless we're given a charge. It's neutral. Polyatomic ions, we use the polyatomic ion charge that we've been given to determine that. So let's look at a couple of these. So CO2. So let's look. What are the rules? The rules say that O, and let me see if I can get my writing tool here. Okay. So the O has a -2 charge. There are 2 of them. And we know that CO2 is a compound, so it has a 0 charge. So I want to know what carbon is. So I put X plus 2 minus 2, and the 2 minus 2 comes from the oxygen, is equal to 0. So X is equal to X minus 4 is equal to 0. So X is equal to a +4. So that means the carbon has a +4 oxidation state while the oxygen has a -2. Okay, pretty simple, right? Okay, let's try another one. SF6. So what's the rule? We look at fluorine. Fluorine always has a -1, I'm sorry. A -1 because there are 6 of them. We've got 6 minus 1. It's a compound, so everything is equal to 0. So what is S? X plus 6 minus 1 is equal to 0. So X is equal to a +6. So the sulfur here has a +6 charge. And the fluorine has a -1 charge. Sorry, I didn't write that very well with my finger. All right, the next one, NO3, 1-. Now this is a polyatomic ion, so that means that all the charges are equal to a -1 because it's a polyatomic. O, again, gets always assigned a -2, so that means I've got 3 times a -2 plus some number we don't know yet. So X minus 6 is equal to a -1. So X is equal to +5. So the nitrogen here has a +5 charge. Pretty simple. It's just an algebraic formula. So you determine the one that you don't know in that formula, in that polyatomic ion or in that chemical formula, from the ones that you do know. We know hydrogen, we know oxygen, we know fluorine. And if we have metals, they take the charge that they should have. Be careful about the transition metals because they're reduced and oxidized quite a bit. Okay. So when powdered aluminum metal is mixed with pulverized iodine crystals, I'm taking away my face again. Hang on, I gotta find it. Oh, I can't find the little thingy. Sorry. Go back. Okay, I hid myself. When powdered aluminum metal is mixed with pulverized iodine crystals and a drop of water is added to help the reaction get started, the resulting reaction produces a great deal of energy. As a matter of fact, it makes nice purple flames. The mixture bursts into flame and purple smoke of I2 vapor is produced from the excess iodine. The equation for the reaction is as follows. And there you see 2Al plus 3I2 yields 2AlI3. For this reaction, identify the atoms that are oxidized and reduced. So we have to go back to our definitions. Remember, oxidized means that it's losing electrons or it's gaining charge. Reduction means it's gaining electrons or it's losing charge. So what we have to do is we have to identify oxidation numbers. So aluminum is its elemental form, so it is going to be 0. Okay, I2 is also its elemental form, so it is going to be 0. Then we come over here and we have this compound. Well, aluminum in an ionic bond is always going to be a +3. And because there are 3 iodines, iodine is a -1. So this one's pretty easy. Aluminum goes from 0 to +3. Well, it had to lose electrons to do that, but it's also gaining charge. So aluminum is oxidized. Okay, I'm using my finger, so forgive the nastiness. Okay, and then I go to I2. Well, I is reduced. I go from having a 0 charge to a -1 charged. So that's how you determine what is oxidized and what is reduced. So aluminum is called the reducing agent, and iodine is called the oxidizing agent, but that's beyond the pale here. I just want you to know what's been oxidized and what's been reduced. Everybody got that? Okay. Next one. Metallurgy, the process of producing a metal from an ore, is always involved in oxidation reduction reactions. In the metallurgy of galena, that is lead sulfide, the principal lead-containing ore, the first step in the conversion of lead sulfide to its oxide, is a process called roasting. So we see the equation for the roasting process. The oxide is then treated with carbon monoxide to produce the free metal lead. It says for this reaction, identify the atoms that are oxidized and reduced. So what do we have to do? We have to determine what's happening. So in the first one, Pb is a +2 charge. Okay, sorry, +2. Okay, S is a -2 because it's an ionic bond. O is in its elemental form, so it's 0. Then we go over here. Well, Pb is still a +2. O is a -2 now. And over here we have to figure out what happened to S. We know that the charge on all of it should be 0. We have 2 oxygens at a -2. So what's the sulfur? Well, it looks like the sulfur is going to be a +4. So the sulfur is going to be a +4, and the oxygen is going to be a -2. So this is what we see. Lead has no bearing here. Lead doesn't make any difference, so we don't have to worry about the lead in this one because it doesn't change charge. So what happens here? S goes from a -2 to a +4. It increased in charge, so that means that S is oxidized in this reaction. Okay, what's happening next? Well, something has to be reduced. O goes from a 0 to a -2 charge. That's getting more negative. That's gaining electrons. So O is reduced. Okay. All right. So we see that happening right there. I'm turning down my little speaker thingy so that doesn't come through again when I get an email. So the oxide is treated with carbon monoxide for the next reaction. So we know, okay, Pb here is still a +2. O is a -2. The O here is a -2, which means the C is a +2. On this side, Pb becomes a 0 because it's the elemental form. And then CO2, well, let's see, CO2, 0 is equal to 2 times the -2 plus X for the C. So X is equal to a +4. So the C goes to a +4. So let's see. O isn't changing because it's a -2 on both sides, so we don't have to worry about the O's. Pb goes from a +2 to a 0. That's being reduced. So Pb is reduced. It is gaining electrons to go from a +2 to a 0. Sorry, that is really hard to see, but that's probably as good as I can get right here with my little finger. Or my big finger, whichever one you want to talk about here. Reduced, okay. And that means that the C going from a +2 to a +4 is oxidized. So carbon is oxidized. So that's the 2 reactions for that problem. So let's see if we can move on and move forward from here. Okay, so balancing redox reactions with the half reaction method. This is a different method for balancing than you've ever seen, and some things can only be balanced using the half reaction method. So the first thing we do is divide the equation into oxidation and reduction half reactions. Okay, that means we determine what's being oxidized, what's being reduced, and we divide them by those things. Then we balance all the elements besides hydrogen and oxygen, so we make sure that all the manganese or all the carbon or all whatever's there is balanced. Then we balance the O's by adding oxygens to the appropriate side. So if there's O on the reactant side, we add water on the product side. If there's O on the product side, we add water to the reactant side. Once we've done that, we balance the H's by adding H plus to whatever side we need to get the H's balanced. Then we look at the charge. Remember, the charge not only includes what's happening to a single atom, but what's happening to any atoms that you have there. So if you have more than one atom of that kind and it is gaining 1 electron, If you have 2 of those atoms, that's a gain of 2 total electrons. So make sure you're looking at this stoichiometric ratio there too. Then, if the number of electrons for both half reactions is not equal, I find the least common multiple and I multiply both half reactions so that the electrons will cancel out. You've never seen a balanced equation with electrons in it, because the whole point of this is to get those electrons to cancel out. Once we do that, we recombine the 2 half reactions. We just add them together, canceling out any common terms from side to side. So if we have water on both sides, we cancel out the waters until we have no water on one side and whatever's left over on the other. All the electrons go away. That kind of thing happens. If it's basic, so that what we've talked about is an acidic solution. If it's in basic solution, after we've put them all together and recombined, we then neutralize any H plus with the same number of OH minus. That turns it into water. And then we cancel out waters from both sides. Okay? After we've done that, we just double check. We double check to make sure we have the right number of each atom, to make sure that we have it done correctly. Okay? This is more complicated than you've ever done. So be patient and hang tight. Okay? So let's do a problem. So assign the oxidation number to all of the following equations and identify the oxidation and reduction half reactions and balance the equation as well. So here we go, assigning oxidation numbers. We have a -1. So we have a -1 charge total here. We have 4 times -2, okay, plus some number. Well, that means that some number is going to be a +7. So the manganese is going to be a +7. We can already see the Fe is a +2 here. So right here, the Fe is a +2. The manganese is a +2. The Fe is a +3. So what's happening? Well, manganese is going from +7 to +2. The manganese is being reduced because it's getting smaller in charge. So that's my first half reaction. I have MnO4 minus, and that's an aqueous form, that's yielding for me Mn2 plus. Okay? The other side of that reaction is the oxidation reaction. I'm going from Fe2 plus to Fe3 plus. I'm gaining more charge. So I have Fe2 plus going to Fe3 plus. Okay, this is where the complication comes in. So in our first half reaction over here with the manganese, I have 4 oxygens. So what I need to do is I need to add 4 waters on this side. Adding 4 waters balances out the oxygen, but now I have hydrogen, so I'm going to add that over here. So plus 8 hydrogen. Okay? So far I have everything balanced. Now I need to look at the charge. This one was a +7. This manganese was a +7. This is a +2. That's a difference of 5 electrons. That means the +2 manganese has 5 more electrons than the +7. So I'm going to be putting 5 electrons on the reactant side. I'm sorry. Oh, it's not working. 5 electrons on the reactant side. Why? Because I have +7 manganese here, +2 manganese on the other side. So I need to make sure that my electrons are balanced. I have 5 fewer electrons on the reactant side. Also, in the reduction reaction, the electrons should always go on the reactant side. In the oxidation reaction, the electrons should go on the product side. So we are now balanced here. We have everything balanced out right there. So we go to the other half reaction. So here's the other half reaction and put a line between them. So Fe2 plus to Fe3 plus. Well, that's 1 and 1. We don't have to do that. There aren't any O's, so we don't have to worry about water. But we do have to worry about the electrons. So Fe2 plus is a lower oxidation state than Fe3 plus, which means Fe2 plus had 1 more electron. So that means I have to add 1 electron on the product side. But now I see, okay, hang on, my electrons are not equal. I have 5 electrons over here, right there, and I have 1 right here. So what I'm going to do is I'm going to multiply this whole reaction by 5 and get 5 Fe2 plus yielding 5 Fe3 plus 5 electrons. The reason I want to do that is because now I'm going to add these 2 reactions together. So 5 Fe2 plus is going to give me 5 Fe3 plus 5 electrons. So I'm going to add those two reactions together. So the electrons cancel out because there's 5 on each side. I did that on purpose. And then I'm going to add it all up. So I have 8 hydrogens that are in aqueous solution, plus 1 permanganate ion in aqueous solution, plus 5 iron 2+ ions in aqueous solution that are going to yield 1 manganese 2+ plus 5 Fe3+, and I should be putting aqueous, okay, plus 4 waters. Okay, so now I'm double checking everything to make sure everything's right. I've got 8 hydrogen over here, 8 hydrogen over here. I've got 1 manganese, 1 manganese. I've got 4 oxygens, 4 oxygens. 5 iron, 5 iron. So everything is good, and this is the reaction. Okay, let's try another one. So balance the following equation using the half reaction method. Here we go again. We know that the manganese here is going to be a +7. We calculated that the last time. Sorry, that's hard to see. +7. Okay, +7. +7. Okay, let's try that. I is a -2 here. Mn is a +2, and the I2 is 0. So it's pretty clear what our half reactions are here, right? We have the permanganate ion with a -1 going to the manganese +2 ion. We have the iodine -1 ion going to I2. Okay, so over here we see we have O's, so we're going to add the 4 waters. Okay, over here we're going to add the 8 hydrogens. Okay, and we still have the 5 electrons, so we have 5 electrons here still. It's the same as the last one, so this half reaction is exactly the same as the one from the last problem because it's exactly the same stuff. On this side, we first have to balance out the I, so we have 2 I's here. So we have a -1 and a 0. There are more electrons right over here. There was 1 more electron for each I, but there are 2 I's, so we have +2 electrons. Well, we see our electrons are not okay. So what we're going to do is this side is going to be multiplied by 5, and this side is going to be multiplied by 2. So I'm going to get 16H plus 2 manganese, or permanganate ions, plus 10 electrons. And that's going to yield 2 manganese 2+ ions plus 8 water. Okay, and then I'm going to add to that this other one. So I'm going to have 5 times 2, I'm going to have 10 I- ions, yielding 5 I2 ions plus 10 electrons. Okay, and I usually, hang on, let me do something really quickly. Let me erase this stuff right here and do what I usually do. I usually line up the yield sign. Why? Because I'm trying to make sure I know the difference between products and reactants. And if I line up the yield sign, then I know that I've done that. So 10 electrons cancel out. Nothing else cancels out from side to side, so I have 16 H plus 2 permanganate ions plus 10 iodine, yielding 2 manganese 2 plus 5 iodine molecules plus 8 waters. So I double check. 16 hydrogen, 16 hydrogen. 2 manganates, 2 manganese. 8 oxygens, 8 oxygens. 10 iodine, 10 iodine. Everything is good. So I'm going to stop right there because your worksheet doesn't ask you to actually balance any equations, but I want you to digest that a little bit, and we'll continue that a little bit more later.